Hello everyone. Welcome to today's presentation. I'm excited to be here with you all. Today we're going to explore 14 elements, compounds, and matters for Class 7th General Science. This session will include some engaging exercises to help us understand these fundamental concepts. We'll cover what elements and compounds are and how they make up the matter around us. So, let's get started and dive into the fascinating world of science. Let's explore the question, who are my companions? On this slide, we see two groups. Group A lists different substances or materials, and Group B shows their answers or classifications. Starting with Group A, we have stainless steel. Now, stainless steel is a metal alloy, which means it's a mixture of metals designed for strength and corrosion resistance. Moving on, silver is also a metal, a pure element, often valued for its conductivity and beauty. Next is the Bajani mixture for milling. This is a specific mixture used in grinding or milling processes, highlighting the idea of mixtures and materials. Salt appears as well, which is a compound, meaning it's made up of two or more elements chemically combined. Coal is listed, and coal is classified as a nonmetal, even though it's a carbon-rich substance. Then, hydrogen is shown, which is an element, meaning it's a pure substance made up of only one type of atom. The overall theme here is understanding how different materials can be grouped based on their properties, whether they are elements, compounds, mixtures, metals, or nonmetals. Recognizing these categories helps us better understand the nature of the materials we work with or study. Let's take a closer look at this table, which connects chemical symbols to their respective elements. As you can see, each symbol is a shorthand notation for a specific element. For example, Zn stands for zinc and Cd is cadmium. These symbols are internationally recognized and help scientists communicate clearly across different languages and regions. Moving on, Z represents xenon, a noble gas used in lighting and other specialized applications. Bromine, with the symbol Br, is a halogen, often found in disinfectants. Titanium, abbreviated as T, is well known for its strength and resistance to corrosion, making it popular in aerospace and medical implants. Copper, or Cu, is a metal we all know for its electrical conductivity and use in wiring. Iron, symbolized as Fe, is essential for the human body and also plays a vital role in construction. Silicon, Si, is the backbone of modern electronics, forming the basis of computer chips. Iridium, is a rare, very durable metal used in high-temperature applications. And finally, TT, which is actually a typo here. It should be PT, representing platinum, a precious metal used in jewelry and catalytic converters. Connecting this to the overall theme, understanding these symbols and their corresponding elements is fundamental in chemistry because it allows us to identify and work with different materials efficiently. Recognizing these symbols helps us interpret scientific data accurately and communicate effectively in the scientific community. Let's take a closer look at some common compounds and their chemical formulas. For example, hydrochloric acid is represented as HCl, which tells us it has one hydrogen atom and one chlorine atom. Similarly, sulfuric acid is written as H2SO4, indicating it contains two hydrogen atoms, one sulfur atom, and four oxygen atoms. Moving on, sodium chloride, which we all know as table salt, has the formula NaCl, just one sodium and one chlorine atom. Glucose, a vital energy source, has the formula C6H12O6, meaning 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. Lastly, methane, a simple hydrocarbon, is written as CH4, with 1 carbon and 4 hydrogen atoms. Now, a key point here is understanding that molecular formulae reveal the exact number of each type of atom in a compound, which is essential for grasping how substances are constructed at the molecular level. This connects directly to the overall theme of understanding chemical compositions and how they relate to properties and reactions. When we talk about molecular formulae, we're essentially decoding the composition of these compounds, which helps us predict behavior and reactions. So, as we move forward, keep in mind how these formulas serve as the foundation for understanding chemical behavior and the relationships between different substances. Let's talk about how buttermilk is churned to get butter and the scientific reasons behind this process. When we churn buttermilk, we're actually separating its two main components, water and fat or cream. This separation is key to forming butter. Churning helps these components come apart because, during this process, the cream or fat globules start to come together. When we stir vigorously, these fat globules collide and stick together, forming a solid lump. This is the butter. The important part here is the role of centrifugal force. Imagine spinning the mixture rapidly. This force causes the fat or cream to collect on the top, creating the solid butter layer. Meanwhile, the remaining liquid, which is mostly water and other leftover components, stays behind. So, by churning the buttermilk, we're essentially encouraging the fat to aggregate and separate from the water, making it easier to collect as butter. This scientific process explains why churning is so effective in butter making. In chromatography, the ingredients of a mixture don't all move the same way. When water rises up the filter paper, each component reaches a certain height and then stops. This happens because two key properties are at play. First, the stability of each substance in the solvent affects how far it can climb. Second, how well the substance sticks to the stationary filter paper also influences its movement. As a result, not all components reach the top. Instead, they stay at different heights, allowing us to separate and identify them. Now, shifting to a different but related idea. When it's summer and the heat is intense, wrapping a wet cloth around a water container is a simple yet effective trick. The wet cloth absorbs heat from the surrounding air, which helps keep the water inside the container cooler for a longer period. This is a practical example of how evaporation and heat absorption work together to maintain cooler temperatures naturally. Both concepts, whether in chromatography or cooling, show how understanding physical properties and processes can help us solve everyday problems more efficiently. Let's take a closer look at the differences between metals and non-metals. First, metals are excellent conductors of heat and electricity, which means they allow heat and electrical current to pass through them easily. This is why metals are used in wiring and cookware. In contrast, non-metals are poor conductors, so they don't transfer heat or electricity very well. Next, metals are generally very hard and strong, making them durable and suitable for construction and tools. Non-metals, however, tend to be brittle. They break easily when force is applied, except for diamond, which is an incredibly hard form of carbon. Metals are ductile, meaning they can be drawn into wires without breaking. This property is vital for making electrical wires. Non-metals are not ductile at all, so they cannot be stretched into wires. Now let's talk about appearance. Metals are lustrous, which means they have a shiny surface that reflects light. This shiny quality is what gives metals their distinctive look. Non-metals, on the other hand, are dull and lack that shiny surface. Regarding malleability, metals can be hammered into thin sheets without breaking, which is called malleability. Non-metals are brittle and cannot be hammered into sheets. They tend to shatter or crumble when force is applied. Lastly, metals are sonorous, meaning they produce a ringing sound when struck, which is useful in musical instruments. Non-metals are non-sonorous. They don't produce such sounds when hit. So, to summarize, metals and non-metals differ significantly in their physical properties, from conductivity and strength to appearance and malleability. These differences help us understand their uses and behavior in everyday life. Let's take a closer look at mixtures and compounds. A mixture is obtained by physically combining two substances, meaning you can mix them together without changing their individual properties. For example, think of a salad or salt dissolved in water. Mixtures are generally impure because they contain more than one substance. One key point is that the substances in a mixture can be separated easily using physical methods like filtration or evaporation. Also, forming a mixture doesn't involve any energy change. It's a simple physical process. Now, on the other hand, a compound is formed when two or more elements chemically combine. Water is a perfect example. Its chemical formula is H2O, which shows that hydrogen and oxygen have bonded chemically. Compounds are pure substances because they consist of only one kind of chemical entity. To separate the elements in a compound, you need chemical methods, like electrolysis, and this process involves a change in energy. So, in summary, the main differences are that mixtures are physically combined and easily separated without energy change, while compounds are chemically bonded and require energy to break apart. This distinction helps us understand how different substances are formed and manipulated in chemistry. Let's look at the difference between atoms and molecules. Atoms are the smallest particles of an element that can participate in a chemical reaction. Think of them as the basic building blocks. Molecules, on the other hand, are formed when two or more atoms combine. An important point here is that molecules do not break apart during chemical reactions. They stay intact unless a specific reaction causes them to break down. Also, atoms may or may not exist freely. Some exist on their own, but many are found combined with others. Molecules generally exist in a free state, meaning they are stable enough to stand alone. Speaking of stability, an atom by itself isn't very stable. It's usually more reactive or eager to bond. But molecules tend to be more stable and can often exist independently without immediately reacting. Understanding this fundamental difference helps us grasp how elements and compounds behave in chemical processes, which is crucial for the overall theme of understanding matter at a molecular level. Now, let's take a closer look at the two methods of separation highlighted here: distillation and separating funnel. Separation by distillation is primarily used for separating solutes from solutions. It works on the principle that different liquids have different boiling points. So, by heating the mixture, we can selectively vaporize one component, then condense it back into a liquid, effectively separating it from the other. During this process, heat is actively applied to facilitate vaporization, making it suitable for separating liquids with significantly different boiling points. On the other hand, separation by a separating funnel is used when dealing with two immiscible liquids, that is, liquids that don't mix like oil and water. This method relies on the difference in densities between the two liquids. Since one is usually denser, it settles at the bottom, allowing us to easily separate the layers by opening a tap at the bottom of the funnel. Importantly, no heat is involved in this process, making it a more straightforward physical separation technique. So, the key difference here is that distillation involves heating and vaporization based on boiling points, while the separating funnel depends on density differences without any heating. Understanding when and why to use each method is essential for effective separation in different chemical processes. Let's talk about how the components of mixtures can be separated using simple methods, with a focus on distillation. Distillation is a very important technique, especially when we need to purify impure liquids. For example, if we have seawater and want to obtain pure water, distillation is the way to go. The process involves heating the seawater in a round bottom flask. As we heat it, the water turns into steam. This steam then travels through a condenser, where it cools down and condenses back into liquid form. The key here is that only the water vapor passes through, leaving behind the salts and impurities in the original flask. The condensed pure water drips into a conical flask, from where we can collect it separately. Meanwhile, the salts and other impurities stay in the distillation flask because they do not vaporize at the same temperature as water. This method highlights how we can separate components based on differences in boiling points, making it an effective way to purify liquids or separate mixtures. It's a great example of how simple techniques can be applied in real-world scenarios, especially in fields like chemistry and environmental science. Let's talk about the separating funnel, which is really useful when we need to separate two immiscible liquids from a mixture. Imagine you have a mixture of two liquids that don't mix together, like oil and water. You pour this mixture into the separating funnel and leave it undisturbed. Over time, you'll notice two distinct layers form because the liquids have different densities. The lighter liquid, such as oil or kerosene, will float on top, while the heavier liquid, like water, stays below. This clear separation is key. To separate one of the layers, you simply open the stopcock at the bottom of the funnel, and because the liquids don't mix, you can drain out the lower layer without disturbing the upper one. For example, this method works perfectly for separating kerosene from water. It's a simple yet effective technique that relies on the immiscibility and difference in densities of the liquids. This process is a fundamental part of many laboratory and industrial separation methods, helping us isolate specific components from complex mixtures. Now, let's talk about some common methods of separation that we use in everyday life and in science. First up is centrifugation. This process involves spinning a mixture at high speeds to separate its components. For example, when we separate skim milk from whole milk, or water from clothes during laundry, centrifugation helps us do that efficiently. Even in the medical field, it's used to separate blood cells from plasma, which is crucial for diagnostic tests. Next is magnetic separation. This method is really useful when dealing with mixtures that contain magnetic materials, like iron fillings. By using a magnet, we can easily attract the iron particles and pull them away from the rest of the mixture. It's a simple yet powerful way to separate magnetic from non-magnetic substances. Then there's sifting. This technique is all about sorting solids based on size. When you sift flour or sand, larger particles stay on top, while smaller ones fall through the sieve. It's a straightforward method to get particles of different sizes separated, which is especially helpful in cooking and construction. Lastly, we have picking and sorting. This is more manual but very effective, where you pick out or separate substances based on specific needs. Whether you're removing unwanted materials or selecting the parts you need, this method relies on careful observation and selection. All these methods connect to our overall theme of understanding how mixtures can be separated into their individual components, which is fundamental in science and everyday life. Let's talk about the elements, compounds, and mixtures we use in our daily life. Starting with mixtures, these are combinations of different substances that are not chemically bonded. For example, we often use lemon and water to make lemon water, or sugar and milk when preparing beverages. Salt and water are common for cooking or cleaning, and cereal mixed with milk is a typical breakfast. We also use cement in construction, soap for cleaning, and alloys like steel and brass, which are mixtures of metals with other elements, making them stronger and more durable. Moving on to compounds, these are substances formed when elements chemically combine. Examples include salt, which is sodium chloride or NaCl, sugar with the formula C12H22O11, and baking powder, which is sodium bicarbonate, NaHCO3. We also use oils, which are compounds made up of various fatty acids and glycerol, essential in cooking and other applications. Now, looking at elements, they are the basic building blocks of matter. Metals like aluminium, copper, iron, silver, and gold are widely used in everyday life because of their properties such as conductivity and strength. On the other hand, nonmetals like carbon, hydrogen, and oxygen are fundamental to many compounds and are found everywhere, from the air we breathe to the food we eat. Understanding these categories helps us appreciate the materials we encounter daily and their roles in our lives. In our daily life, centrifugation plays a surprisingly important role in many of the activities we do. For example, when we make buttermilk from yogurt, we often use a stirrer, which relies on the same basic principle of separation by spinning at high speed. This helps us extract the liquid part and achieve that smooth, creamy texture we enjoy. Another common use is in washing machines, where the spin tub rapidly rotates to dry wet clothes. The centrifugal force pushes the water out of the fabric, making drying much quicker and more efficient. In medical science, centrifugation is vital for separating different components of blood. When blood is spun in a centrifuge, the heavier blood cells settle at the bottom, while plasma remains on top. This process is crucial for diagnostic tests and treatments. And even in amusement parks, the working of roller coasters involves the same basic concept of centrifugal force, keeping us securely in our seats as the coaster speeds through loops and turns. So, you see, centrifugation isn't just a scientific concept. It's something that touches many parts of our everyday lives, making tasks easier and more effective. Now, let's discuss where we use the methods of separation by distillation and by separating funnel, and why. First, distillation is a very common technique used to separate a solute from a solution. It's especially useful when we want to purify a liquid or remove impurities. For example, when we need to remove salt from seawater to make it drinkable, distillation is the method of choice. It works by heating the seawater until it evaporates, then condensing the vapor back into pure water, leaving the salt behind. Next, let's look at the separating funnel. This method is ideal when we have two immiscible liquids, meaning they don't mix, like oil and water. When we need to separate such a mixture, the separating funnel allows us to easily isolate each liquid based on their different densities. For example, if we want to separate oil from water or a mixture of kerosene and water, the separating funnel is very effective because it exploits the differences in their physical properties. So, in summary, distillation is used mainly for purifying liquids and removing dissolved substances, while the separating funnel is used for separating immiscible liquids based on their physical differences. Both methods are vital in different contexts for achieving effective separation in chemical processes. Now, let's talk about some important precautions to keep in mind when using distillation methods and separating funnels. First, during distillation, it's crucial to have a well-organized workspace. Make sure your area is well lit and well ventilated to prevent any buildup of alcoholic vapors, which can be hazardous. Also, keep a fire extinguisher nearby, safety first. And importantly, check all the piping involved in the process. There should be no obstructions, because if pressure builds up in the stills, it could cause them to burst, leading to accidents or spills. Moving on to the separation funnel, safety here is just as critical. The stopper must be tightly fitted to prevent any leaks when you invert the funnel. A loose stopper can cause the solution to spill out unexpectedly, which is dangerous. Finally, never discard any layer of liquid until you are absolutely certain that you have isolated the final product. Rushing this step can lead to losing valuable material or contamination, which could compromise your entire experiment or process. So, always remember these precautions to ensure safety and accuracy in your distillation and separation work.